Hello, everybody. So what we're going to be looking at today is going to be section 10.3 in the book. That was a loud car. Um, and what is this going to be about? Well, this is going to be about how we can represent a graph in other forms than just the picture, and also something called isomorphism. So isomorphism is a pretty complicated, not complicated, I don't know why I'm saying that. It's a pretty important concept. You'll see it in a lot of math classes if you take more math classes, and probably computer science classes as well, but I'm less familiar with that. So let's go ahead and get started. So what I want to do first is I just want to draw a graph. So we just need some vertices here. We're going to use 5, A, B, C, D, E. All right. We need some edges. I'm drawing the one that's in the book. Oops. We can do better. All right. So there's a graph. It's just a simple graph. It's even labeled that way, a simple graph, right? And if you wanted to describe this graph to somebody, how would you do it, right? So we're not going to give them the picture. We're going to have to tell somebody how to make this graph. Um, and so what you can do is you can write an adjacency list, for example. You can represent this graph as an adjacency list. And we don't really care about these, so don't um, put too much stock into it. But hold on here, let's get a highlighter. Adjacency list. All right. So what is an adjacency list? So I'll write one down and you'll see exactly what it is. So if you just say, vertex, and then you say adjacent vertices, then this will give you everything you need. So what you do is in the column for the vertex or for vertex, you just put all of the vertices that you have. So you just say, well, there's A, there's B, there's C, there's D, there's E. Those are the vertices, right? So this is just a list of the vertices. In the graph. And then in the other column, you just list all of the vertices that they are adjacent to one by one. So of course, when you're doing A here, um, A is adjacent to B. There's an edge there. C, not to D, right? There's no edge from A to D, but then E. So B, C, E. B, C, E. And that's it. And so you just do that for every vertex, and then you have your adjacency list. So B is just adjacent to A. A. C is adjacent to A, E, D. So A, D, E. A, D, E. D is adjacent to two vertices, C and E. C, comma E. Like that. E is adjacent to C and to D and to A. So A, C, D. It doesn't matter if you write them in order. I just am. All right. And there you go. That's an adjacency list. You can do this for directed graphs, which you just would have to pay attention to what is the initial vertex and what is the terminal vertex. And basically what you would do is you would just change this column to initial vertex and this column to uh, terminal vertex, terminal vertices. So let's just do one example of that. Directed graph example. So I'm not going to make this too complicated here. Arrow, arrow, arrow. And then let's just do A, B, C. Let's just, one more. Let's do D. D. There. Okay, now we're done. So what would it look like? So you make your table just like before, but now you have initial vertex, and then you have terminal vertices. Use the plural because, usually there's more than one over there, or there can be at least. So your initial vertex, again, is just a list of the vertices in the graph. So A, B, C, D. And then your terminal vertices are just where does the arrow point, right? So from A, we have one going to B and one going to C. This one does not count, right? Because this is going to A and we're only looking from A. So A to B, A to C, that's it. So BC. And then for B, B only has one arrow out. It goes to C. C, B to C, A to C, D to C. Nothing actually leaves C though. So there are no, C is not an initial vertex for anything. So this is just empty. So we're on D, D to C and to A. So that's it. So that's how you would do a adjacency list for a directed graph. Okay, so now what we want to do is we want to change this because we don't normally bother with adjacency lists. We normally bother with adjacency matrices. Adjacency matrices are going to be better for representing a graph on a computer. So I'll just go down to the next page. No, I won't. I'll do it right here. So adjacency matrix. So we'll spend more time with this. Adjacency matrix, or matrices in this case. All right. So what is an adjacency matrix? So we'll have a more formal definition here. So it's a pretty simple concept, but it'll look kind of like a pain when we write down the definition. Suppose we have a simple graph. Suppose we have a simple graph. That's important. We want to be able to do adjacency matrices for other types of graphs as well, but right now we're talking about a simple graph. Remember, no multiple edges, no loops, that kind of thing. So we have a simple graph, G, which has a vertex set and an edge set, with magnitude of V is in. So what does that mean? So remember, V is the vertex set. So the cardinality of the vertex set, that's literally just how many vertices are there, right? Number of vertices. All right, so that's an N. Okay, so we have that. So what are we going to do with it? So what we want to do is we want to list the vertices as V1 through Vn. So we'll say called V1, V2, Vn. Okay. Now, what if they're called A, B, C, D? Well, that's fine. You just need to decide on the order, right? Like A can be V1, B could be V2, C could be V3, and so on. So we've got these vertices, and then what are we going to do? So here's the definition. So definition, the adjacency matrix. That doesn't say adjacency matrix. Try again. The adjacency matrix of A of G is the matrix M by N matrix n by n matrix with a 1 in the I comma j spot if vi and vj are adjacent. Okay, so in words it's a little bit tricky. In symbols it's also tricky. So here's another way you could say it. You could say for a ij is the matrix with aij equals 1 if vi comma vj is an edge in G, and 0 if, well, otherwise. Now, I want to say this too. This definition already looks complicated, and it is not. Okay? Seriously, this is a very simple thing to do. All right? So, like, here's an example, and you'll see that it makes perfect sense. So, A, B, C, D. We need some edges. So let's go here, 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 here. All right. So those are edges. And if you want to write the adjacency matrix, let's do it. So write out adjacency matrix for this graph. All right. So here's what you do. So first of all, it's a matrix, which you must have written at some point in your life. Not, here's a reminder of what a matrix looks like. If I can draw straight lines. Okay, so we're going to have a matrix, and basically just do this. So we want to think about, here, let me pick a light color. Just go like this: A, B, C, D, A, B, C, D. And we're just going to fill out these spots based on whether there's an edge between the vertices. So, right, there's an edge between A and B. So you go to the spot A, B, and you put a 1 there. And then there's an edge between A and C. So you go to A and C, and you put a 1 there. And then there's an edge between A and D. So A, D. So you put a 1 there. Now, look at A. Is there an edge from A to A? No, there's no edge from A to A, right? So this would be a 0. All right, so that's the first row done. So then you go and you do the second row. So what about B? What is B adjacent to? So B is adjacent to A. So you have the BA. Now, this is an undirected graph actually. So if AB is an edge, then you end up with a 1 here because of AB, but also BA, right? AB and BA are the same thing. So if there's a 1 here, there's actually going to be a 1 here. All right, what else? B is adjacent to C. So we're looking for BC. There's a 1 there. That's it, right? B and A, B and C. There's no BB. That'd be a loop. And there's no BD because, well, we don't see it. So those are zeros. All right, what about C? So for C, C and A, so CA, C and B, so CB, no CC and no CD. So 0, 0. All right, last one. D, there's DA, DA, no DB, 0. No DC, so 0. No DD, 0. All right, and there you go. That's your adjacency matrix. So the letters that I wrote on the outside are not actually part of the matrix, right? So, you can just cross those out if you want, erase them. You don't need to write them is what I'm saying. But there you go. So that is your adjacency matrix for that graph. And so the nice thing about this is that this is a really convenient form if you're going to try to store a graph into a computer, right? Like for example, in MATLAB, if you want to try to write out this graph, how are you going to write it? Well, an easy way to do it would just be store the matrix. And maybe the matrix is going to be enough information about the graph. So we like adjacency matrices. Okay, so those are pretty easy. Now, what are we going to do if, let's see here. What are we going to do for multiple edges and for loops? Okay, and we also define that. So let's talk about that. Multiple edges and loops. In adjacency matrices. All right, and so it's not actually that complicated. So let's just talk about these in order, right? So let's talk about, oh, I said multiple edges and loops. That's true. Let me change this a little bit. Multiple edges, loops, and directed edges in adjacency matrices. All right, so let's talk about what to do there. So multiple edges is going to be pretty easy. Instead of a 1, you just put the number of edges. So that's easy, right? So instead of a 1 in the matrix, you put in the number of edges. Easy enough. All right, what about loops? Now, the only problem with loops is you have to decide what number to put into the matrix, right? Like, so like, let's say come back to this graph here and like I put a loop on the D, right? Now you would say, okay, well, that's an edge from D to D. So you would say, go to DD and you put in a number, right? But what number? So here's the thing. If you put in a 1 because there's one edge, then, right, because there's one loop there, one edge from D to D, then the number of edges, no, that's not what I want to say. Then if you add up this row here, you get 2, right? If you add up this row, you get 2. If you add up this row, you get 2. Now here's the point of that. If you add up the row for C, you get 2. And that's because the degree of C is 2, right? One edge, 2 edges. So the degree of C is 2. So you sum that row, you get the degree of C. But if you sum the row of D, you also get 2. But the degree of D is not 2. Because if you remember the degree, the definition of degree, a loop counted twice for degree. right? So the degree of D, the way I drew it, is actually 3. So if you put a 1 there, then this sum is not going to be the degree of D. And that's kind of bad. The reason I'm explaining this is because there's multiple conventions here. There are some books and people that would put a 1 here because that is one edge. But then they will not have a theorem that says that the sum on this row is the degree of D. There are other people that would like to put a 2 here because then the sum of this row would be a 3, and the degree of D is 3. So it's kind of, what are we going to do? It's a good question. I don't remember. So let's let me read the book and see what it says. So let's see. Loops. Where does it say loops? There we go. There we go. So according to our book says specifically a loop is a 1. So if there's a loop on, vi, then, vi, gets a 1. Right? And of course, you have to remember your rule for multiple edges. Of course, multiple loops will be more than 1. Would give you higher numbers. Multiple loops would give you higher numbers. All right. So we are going to put a 1 there, right? We are going to put a 1 there at VII. Now, what about directed edges? There's also nothing special about directed edges, except that you just have to remember what the convention is and remember like how the matrix is defined. So, just if there is an edge, from VI to VJ, right? Then there should be a 1. In the AIJ spot, right? But not the VJI spot, right? Unless of course that is an edge. VJ to VI is also an edge. And really what that means is you just have to think about, rows and columns of your matrix, and it's really easy to get it backwards. So let me draw one here. It's actually kind of funny because I'm looking at the book and they don't have a single example of directed edges or anything for an adjacency matrix. So let's do one here. So before we do it, let me just do this. So if I have a matrix like this, right? So I'm just drawing a matrix here, and you have a spot. Like if you have, number, lots of numbers, and then you have some, spot that we're going to call like, A, I, J. Remember that, A, I, J, I is the row, J is the column. Okay. So rows, right? This is row 1, row 2, dot, 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 row, I'll say in. And this is column 1, column 2, dot, 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 column, in this case, in, right? Because it's symmetric. So you just have to be careful that you know that you do the row first and then the column, right? So you go this first, then this, row, then column. So just get the index right. So be careful to do row first, before the column. For directed graphs, is the only place where it will matter. All right, let's do an example. There. Oops, how did that happen? Okay, good enough. A, B, C, D. All right, so we want to write the adjacency matrix. Let's put a loop. Okay. Yeah, okay. So let's find the adjacency matrix. So we're going to draw a matrix. Okay, so there's our matrix, and we want to do this. So we're doing this, same idea, A, B, C, D, A, B, C, D, right? Or V1, V2, V3, V4, however you're numbering them. And then let's do this. So if you're looking at vertex A, right, you have B to A that doesn't count. We're going A to C. So from A to C, there's an edge from A to C, right? So there's an edge from A to C. So that would be here. Get a different color. That would be here, right? Because this is the from, and this is the to, right? Because this is edge AC, right? AC is edge. A comma C is the way they would write it. So that's row A and column C. So that's all. You just have to put it in the right place. And that's the only one. So you go 0, 0, 0. And then for B, there's B to A. It's here. That's it. So a bunch of zeros, 0, 0, 0. So then you're on to C. C is only a terminal side. There's no C to anything else. So C is actually 0, 0, 0, 0. And then D, we have D to B. That's there. And then also we have D to D, which is 1. Okay. So there you go. Now, yeah. The only thing that's probably kind of confusing there is the loop, because that's a directed edge, and it's also a loop. But don't think too hard about it, right? One loop's supposed to be a 1, so just put a 1. All right. So that's how you would do the adjacency graph for a directed graph. We didn't do multiple edges, but if you want to make one up, we can add an extra one here, do that. And then you would just say, okay, well, that's another edge from B to A. So where's BA? So you find BA right here, and you say, okay, that's a 2. There we go. Now we did directed graphs. and loops and multiple edges. So again, you've got this adjacency matrix here, which really tells you everything about how the graph looks, right? It doesn't tell you where you drew the vertices, right? Like A, B, C, D. But if you draw any four vertices called A, B, C, and D, and you had these, it would tell you exactly where to draw the edges, and it would tell you how many edges to draw, right? So this is a complete representation of this graph. And that's what adjacency matrices are for, right? Adjacency matrices are a good way to store a graph in the computer. Right? It's not the only way. You can literally list out all of the you can literally store a list of edges, and you can literally store a list of vertices. And your edges could just be like a pair. Like if you had 1 comma 2, that would mean an edge between vertex 1 and vertex 2, for example. But this is another way to do it, and it's useful for certain computations and stuff. So these are good. So those are adjacency matrices. What are isomorphisms? We want to talk about that. So what is it? So, also we need incidence matrices. Okay, well, I mean, do we want to? Yeah, okay, let's do incidence matrices and then isomorphisms. So an incidence matrix is a different type of matrix, which is why it has a different name. Basically, what we're going to be doing is we're going to be storing, we're going to have vertices and edges, and we're going to put a 1 in a matrix if the vertex is actually part of the edge, for example. So incidence matrices. So why would they need a second type of matrix for this? Well, I mean, maybe it's going to be, a more convenient form for certain computations. I don't know. But what is it anyway? So definition. So again, we're talking about a graph. So let G equal V comma E be a graph, undirected graph. With in vertices. So I'm just going to say vertices V1, V2, dot, 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 to Vn. And then also there's going to be edges, and edges E1, E2, dot, 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 EM. So we're going to actually be talking about the specific edges. Okay, so then what you do is define your matrix this way. So the incidence matrix, we're going to call it M, and the little entries are going to be IJ again, is the N by M matrix width. And so Mij is going to be, it's a different formula here. It's a 1 when edge EJ is incident with vertex VI. Why I'm putting the VI there? Oh man. And then it's a 0 otherwise. So this would be used if you have a graph where the edges have names for some reason, and maybe that's a convenient form to have it. So let's go A, B, C, D. Now I could number these again, but I'm sticking with lettering here. All right. So what about these edges? What are the edges called? Well, let's just call them E1, E2, E3, E4. Okay. So here's my graph. So for your matrix, write the incidence matrix. Going to be like this. So M equals, you know what? I have the same number of vertices and edges here. I want to add another edge then. Um, let's just add one right here. Call that E5, right? Because they don't have to be the same this time. Okay, so the idea is this. So you put your vertices along the edge. A, B, C, D. Didn't space those very well. A, B, C, D. Right, so these are your vertices. And then your edges go across the top. E1, E2, E3, E4, E5. Right, so they don't have to be, it's not a square matrix this time. Right, 5 edges, but 4 vertices on this one that I drew. But then after that, it's about how you would expect, right? Like so, so this row A is part of E1 and E5. So E1 and 5. So you just say, okay, A is part of E1 and A is part of E5. But that's the only edges that it's part of. So the rest of these are zeros. So then you say, what about B? B, vertex B is part of E1, E2, E3. So 1, 2, and 3. 1, 2, and 3, but not 4 and 5. C is part of E3 and E4. E3, E4, but not the rest. D is part of E2, E4, E5. So 2, 4, 5. So we got 2, 4, 5, and a couple of zeros. All right, and there you go. There's your incidence matrix. What else can we say about this? This would not have a problem with multiple edges because every edge is its own edge. So every edge is its own edge here. And, multiple edges would just add more columns that you'd have here. So that's fine. Actually, let's just, let's see here. What do they say? They say multiple edges. Maybe I'm about to contradict myself here. What do they say? Multiple edges, columns with identical entries. Because the edges are incident with the same pair of vertices. Oh, okay. Who cares? Yeah, there's not a lot to say here. Multiple edges would give some columns would be identical, but that doesn't tell you how to make them. It's just a result. Loops. What would happen if you had loops? If you had a loop, then that would be just a column with only one number in it, only 1, 1. Right? Like if you look at these, if you look at a column here, 1, 1, right, adds up to 2. 0, 1, 0, 1, a 1 and a 1. E3, 0, 1, 1, 0, right? 2 1s, 2 1s, 2 1s. Why do you have 2 1s? Because every edge has like starts somewhere and ends somewhere, right? So of course you're going to end up with 2 1s in every single column, except if you have a loop, because a loop is only going to be between a single vertex. So column with a single 1 would automatically be a loop in that case. Yeah, that's about it. So yeah, that's it for adjacency matrices and for incidence matrices, which of course are different kinds of matrices. So what we need to talk about now is isomorphisms, but I'm going to, well, I can give you the definition here, but we're going to have to do a supplementary lecture for this. So I'll give you the definition and then we'll stop this lecture. All right. Does that make sense to do? Because I'll have to do it at the beginning of the next video. Um, yeah, you know what? I think we better stop right here. Save it all for the next video.